Got it.
Tell me where I have, what frame do I have?
You have pretty much the whole board.
Pretty much the whole board. Okay, good enough. So we have decided that if we have this, we probably have something in the time domain that does this. Do I know for a fact that it comes down to 0?
Yes.
Okay. So anything that does this. Now, do I probably have too much ringing for the amount of this?
Did you move the review session into here?
No, it was just that somebody else was coming into there and there was another question, so essentially, yeah, we did. That's exactly what we did. So probably have too much ringing here. But if I had this, what else could I have?
It would have to not go to 0, it would have to be some other.
Yeah, in fact, it has to not go to 0. It has to go to some other value. Yeah. Okay, if I had this, what would I get?
Higher frequency, more ringing.
Higher frequency, more ringing. If I had this, it's more like this. Or, oops, something like that. So less ringing, lots less ringing. And in fact, I mean, it can be because of where it hits here that there's very little overshoot altogether. That the ringing peaks very close to where this comes down lower. Now, this also brings us a little bit to another question that he had or seemed to have, is how can we get numbers out of this? Could we get numbers from this line to get the rate of decay or the time constant?
Yes.
In fact, we can get the time constant directly when this hits what of the original value?
37%.
Yeah, 37% of the original. Now, notice that that original, the waveform never reached that, ever. It never got up that high. It was the exponential decaying envelope of that which would give us that. But when that exponential decaying envelope reaches 37% of its final value, then we would have one time constant in time. Then how would we find our A term from that?
It's the inverse.
Can we find the B term?
You find a period.
If we had enough here to find a period, which might be enough just in that, if we had enough to find a period, then we could say that the F is equal to 1 over the period, and the omega, which is equal to the B, is equal to 2 pi times F. So yeah, if we could get some information from the drawing, we could figure out what A and B actually were. Continuing on, however, to the next thing. Go down to number 7 on spring 15. This closed book sheet. What's the difference between this and this? What does this give you?
Multiplied by T.
Yeah.
Do I know the slope?
T.
Let's see what it is.
But I don't know the coefficient in front of the t.
Yeah.
So I don't actually know the slope. I don't actually know the slope. So it can be a gentle slope, it can be a very steep slope, it can even be a negative slope. We don't know that. But that's part of the signal. So let's just assume one for a moment. Now, what else am I going to get out of the ground that due to this?
Sinusoidally decaying.
Oops, that's way. And notice that now it's skewed up or down or whatever that linear slope is. Usually that linear slope will start at 0, but it can start other places, which might make you think that there is a pull at the origin, and I probably wouldn't fault you for that, but it could also be initial conditions. And then this will cause some sort of ringing, probably to start at 0 like that. Okay. So that was F and the one beneath it, or I'm sorry, 4 and the one beneath it, 7. So if we're trying to find these in the answers, which one of the answers fit? Any of these answers fit on this side of the page? But none of them are ringing. All the ringing answers are on this side of the page. Which one fits?
Top right.
Top right looks good. Is there another one that seems like it might fit?
2 below that.
Does this one fit?
It's growing up.
So what would have to be in the polls to get this result here?
They have to be on the right.
It's be on the right hand side.
No. Because what is the growth on that one? Is the growth exponential? It's linear. So what do you have to have? Have double poles here and here. So that would be double, double, double. Is there one answer like that? Or one problem like that? There isn't. There isn't a matching one. So sometimes going to the signals doesn't. So what's the only remaining answer that could be? Yeah, this one right here. So that makes it the Y, U rather. Okay. Where are we at? Oh yeah. So we've talked about that kind of, we talked about this. Okay, this. Could be, yeah. He says I could have something like this. Let's see, it must go back down to 0. Why must it go back down to 0?
You don't have a pole at the origin to give it a DC offset.
Yeah. So is there an answer like that?
Yeah.
Which one?
You have a couple. N.
N. Yep, I'll buy N. N is a good answer. Any other answer that might work?
L?
L, yeah. L could also work. L could also work. It just starts at a different value in that case. It starts at some, in that case, the coefficient in front of the fast part of the faster part exponential is the same, not the same value as the.
But F could not work because that has ringing, which would imply imaginary
Yeah,
or complex poles.
yeah, so F would not work. Okay, good. This one, the last one on the front page.
See, that's the difference between the poles in L and N though, because it says the answer is N. How do we determine the difference between those?
I believe when I was doing this, I accepted both answers because the other one is also a possibility.
Okay.
Yeah. Because it goes to 0, it has obviously 2 exponentials. It could be ringing, a small amount of ringing, but most likely it's the same sort of thing. Yeah. So as I recall, I accepted both answers, even though N was the one I was thinking of at the time when I made the problem. Let's see, this one I've got on the board, the one I just drew, with a single pole.
Nonsensical.
Yeah,
No.
we cannot have that. All of our poles must be either on the real axis or they're complex conjugates of one another. Because if that's not true, then we end up with complex numbers in the time domain. We cannot have Now things get a little more interesting on the other side. We are looking for, well, that was not very interesting. There's two here. What am I looking for here?
Steady state sinusoids.
Steady state sinusoids. What's the difference between this one and this one?
Frequency,
Which one's the higher frequency?
the one on the right.
The further away poles. So it should answer, what do you think we're dealing with here for answers? There's a steady state sinusoid, there's a steady state, there's a steady state. R and Q. Which one's R and which one's Q?
R's on the left.
Q. How come S doesn't work?
There's a DC offset.
You have to have pole 0.
So it matches which frequency? It matches this frequency. So would this be S? Evan says no. Would that be S term? So what I've got is same frequency as this, which we called the one before, but it has a DC offset. Jody, you say yes? Yeah, I would agree with Jody. We have that pull at the origin, suddenly we can have that DC offset. Let's see, that's not the most likely case of any real system. The most likely case of any real system producing, has poles like that, would be something like this in the time domain. Oops. Like that. Most of our systems start at 0. And we've noticed that when you do your partial fraction expansions, you've noticed it's very, very common to get several things that are exactly the same number but opposite signs. And that kind of creates that cancellation, which makes the starting value equal to 0. Let's see. So this was a steady state sinusoid. What happens when we get this? Oh, first, what if I double these? What kind of increase?
Linear.
Linear. Back to single poles, but now they're in the right half plane slightly. What happened to my increase? Yeah, now it's going to go exponential. It's going to go exponential. So for the one I've got on the board right now with the exponential increase, which one matches? Is there anyone? No, none of them match. Kind of Y matches, yeah. Yeah, Y matches. Y matches, this one here. For the linear increase, which one matches?
W.
Yep. How is this different?
Which one?
X. If you can't see from the back, move up to the front row. Just I don't have, I'm not gonna draw all these.
You get double the origin.
On the
Yes,
left.
you'd have also a double at the origin.
Yeah.
Now, a double here, a double here, and I think we already talked about that. Okay, good enough. Now, it also asks, list those numbers that are unbounded. So, those numbers are on the other side. So everything associated with unbounded, what are we looking for? Poles on
The right half plane.
right half plane or
Doubles on the.
doubles on
imaginary.
the imaginary axis. List those numbers so that do not converge.
It's not.
Any-
So
any-
does it include everything that we've already listed in part B?
Yes.
All that are unbounded do not converge, right? By, absolutely. There's no way we can have an unbounded signal that does converge.
It's in between the two tables and the gap by the, it's on top.
Oh, I never have found
By the
that.
paper.
By
It's still
paper,
not.
on
Oh,
top.
there, on top. Okay. So, and so all of the same numbers are repeated, but what does also not converge?
Anything with.
The sinusoids. Yeah, the sinusoids that are constant sinus, that don't blow up, but they're steady state sinusoids. List those numbers that could result from exciting a system at its resonant frequency. What are we looking for? Exciting a system at its resonant frequency.
Oh, double poles on the J omega axis.
Double poles on the J omega axis. So this one here, doesn't really matter if that's existing or not, but double pole here, and it doesn't matter where they are. But if you get double poles on the J omega axis, that's exciting a system at a resonant frequency. List those letters on the answer sheet that could be the step response of a BIBO system. Step response of a BIBO system.
So that removes any sinusoidal output, right?
Yes, any steady state sinusoidal will be out. Best just to go through. Could that be the step response of a BIBO system?
Yes.
Yes.
Yeah, it happens to be a BIBO system that has a zero where? At the origin. This one, same thing. Could this be the step response of a BIBO system?
Yes.
Yes, this one.
Yeah.
That one happens to be a system with a origin or a zero at the origin, right? Could this one? Could that one?
No,
Why not, Jim?
because it doesn't, it
Doesn't converge.
Which one? H?
H.
Okay,
H,
yeah.
yeah, does not converge. This guy?
Yes.
Yes?
Yes.
Yes?
Yes.
Yes? Yes?
No.
No.
P does not.
No.
Okay. This one's a little harder. It doesn't blow up. It's not
Right.
unbounded.
If it's a BIBO system, that can be part of the system and it's not a step response.
Yeah, this could be the sinusoidal response of a BIBO system, but not the step response of a BIBO system.
Because that would.
Because this BIBO system rings constantly. So it had to have poles on the J omega axis. This one, this one, this one, all no's. No, no, all deconverging. So everything on this side of the page is a no. Quickly, another thing here. Another test problem. So let me do this real quick. This is how it often shows up, is this. This is time domain. Am I still in frame here?
Yep.
What question is this?
This happens to come from S13, closed book part, number 3. I often give these problems with the little dotted lines in them to help you see what you need to see. Usually that means individual signals. So in this case, if the signal were simply that decaying exponential of the dotted line, what kind of a pole would that require?
You pole on the real axis fairly close to the origin.
Why do you say fairly close to the origin?
It's really slow decay.
It's a slow decay from our perspective, yeah.
And
So does that have to be there even though there's other poles?
Yes.
Yes. Because we construct the signal out of simpler signals. What's the other signal that we're constructing with?
Steady state sinusoid.
Yeah. Next one.
Double at the origin.
Again, the dotted line by itself tells you what?
You're linearly increasing.
Which means?
Double the origin.
What's the other part of it look like?
Decaying sinusoid.
Yeah. Could it be decaying linearly? Is there a possibility for a linear decaying sinusoid?
You have to start it, well, yeah, you can't, there's no start and end points that would work for.
Yeah, there's nothing that works. Nothing that will make you linearly decaying, so it must be an exponentially decaying sinusoid, decaying fast or slow? Fairly slow. Like that. Okay, if I said, instead of what is the poles of the signal, but what are the poles, if this is the step response, what are the poles of the system, what's different?
Yeah.
We lose one right there. We lose one right there. That's the difference. So if I ask you about the system, and typically I would ask you the step response, remember that we lose one pole at the origin because that came from the input rather than the system. Next one. This is hard to draw. Okay, all the dotted lines here indicate individual signals that I have to worry about.
There's a pair and then one.
Yeah.
What do you mean by there's a pair and then one?
The top and the bottom form an envelope.
Form an envelope. So that's another way that I use the dotted lines, is to show you an envelope of a signal. So you can tell whether that envelope is linearly or exponentially decaying or something like that. So that wouldn't be an individual signal, it's just showing you how the shape of the envelope is. So, is there an individual signal that we gotta take care of?
Mm-hmm.
Which one is that?
Yeah, decaying exponential and a step.
Yeah, so I have to worry about this one right here. By itself, this one gives me what poles?
2 on the real axis. 1 at the origin.
And then the decaying exponential? Like that? Exponentially decaying sinusoid, put it that way. It's fairly high frequency, so they're fairly far up there. Yeah. Get the general idea? So it's all about being able to add and subtract signals, creating time domain signals out of individual pieces and what those individual pieces look like. There's really a pretty standard subset of kind of signals that you can show up. I do not ever put triple poles on these things. So we're dealing with double poles. Almost always, if there are double poles, it would be right on the j omega axis because we have special things we know what to look for there. Other than that, if you have complex poles, and then on the left side, we have decaying sinusoids. On the right side, building sinusoids. Double on the real axis would be linearly expanding sinusoids. Singles on the real axis, just constant sinusoids. Anything on the real axis turns out to be an exponential or at the origin step. Right-hand side, going up exponentials, left-hand side, decaying exponentials. So you have basically that subset of stuff that you have to deal with. There is a page in the book, in Bodson's book, where he puts it all in one picture.
Mm-hmm.
You might want to reproduce that picture on your paper if you're having trouble with that. Bodson's book, probably in chapter 2 toward the end. I'm sorry, yeah, chapter 2 toward the end of chapter 2. Unless you've got it folded around weird.
This one?
Yeah. That's the picture right there. It's on page 36 of Bodson's book. It's step responses versus pole locations. It doesn't matter if it's step response or signals. Signals versus pole locations, I think, so. Oh, I see. The only thing he doesn't do is add the input pole. So these would be the system poles, and then if you add that extra pole at the origin, that's when you get these results. Now, there's another picture I'm thinking, this is in chapter 3. There's a chapter 2, it has a circle picture.
Oh, okay.
Oh, that's the next page.
Yeah.
Page 7 has that plus the doubles, but that's not the circle.
I think it was in chapter 2, because that's where he starts talking about signals. This is in chapter 3. Going back to chapter 7, this is all transfer functions. Oops.
Oh, here you go.
You find it?
Yeah. This one I'm thinking?
Oh, I guess it's not a circle. Nope, that's the systems. Nope, that's all right. So this is page 7. Page 7. And he has basically here what the different things look like. And he hasn't shown the complex conjugates of the poles. When they're on complex
Yeah.
conjugates. Which is a little screwy, but that's the kind of thing that we're looking at. But it's also a matter of putting them together in the various possibilities. Because what the poles do not give us. Well, let me ask you. The poles give us some idea of the shape and what the signal is constructed of. But what information is absolutely not included in the poles? Pardon me?
Magnitude and the sign.
In the magnitude. Yeah, the coefficients that are in front of those pieces. And that includes the sign of those coefficients. So we don't know if it's going up or it's going down or it's big or it's small. We don't know those things. And there's another thing that also doesn't show up in the pole locations. Any information that may come from initial
Initial
conditions.
conditions.
Initial conditions. That will not show up in the polls. Okay. Other things that we should look at?
We don't need to, we should still know, like, op-amp stuff, right? Like, or,
For the feedback loop?
yeah.
No. If I do a feedback loop kind of problem, it will be a feedback loop kind of problem like one of these. Let's see if I have an example here, like something like that.
Like a loop within a
Okay.
loop?
Yeah, loop with some sort of
Okay.
things. This is what I would do. I would not give you the op-amp. The deal with the op-amp problems in that homework assignment was I wanted you to start to relate the things that you've seen feedback before into how do you look at it in terms of a block diagram. And in fact, homework 1 also kind of emphasized that point, is that these block diagrams that you write on the board so simply and so easily, sometimes really hard to get from real life and how they fit together. So no, I would not do that. Now, later on in another exam, we'll actually look at how we can do compensators and stuff using op-amps. That's a different question, it'll come later on. So we'll see op-amps and use op-amps again later. Let's see, let's take so this kind of stuff, you'll have something in this realm, for sure, something. Some of that, because I consider that important. Let's see, transfer system functions. I've asked that before, BIBO, as long as you know where the poles are, you can figure that out. Partial fraction expansion doesn't show up as much in recent tests. Let's see.
It will.
The steady state sort of stuff, especially DC gain, factor stuff, so that's pretty well all stuff that we've looked at. This test, all stuff that we've looked at. Okay, this is something I think we did the other day, but I wanted to put it on the board real quick to kind of give you an example again and look at this. Not sure if it was this problem we did or not. Okay. X of t equals 3 e to the minus 9t. Y of t equals 1 plus 4 e to the minus 6t plus e to the minus 9t. This is actually the one I did the other day. So we'll do a quick thing of what can we do about this. Find h of s. How do you do this kind of problem?
Can you just take the Laplace and then multiply them?
Okay, let's take the Laplace. Almost. What's the Laplace of this?
Let's see, 3 times 1 over s plus 9.
What's the Laplace of this?
4
1 over
times
S.
1 over.
Let's get all the pieces. Start with the
1
first
over
piece.
S
One over S.
plus 4 over S plus 6. 1 over S plus 9.
Okay, is that the form we normally look at your Laplace?
Yeah. No.
We need
We
common
need, we
denominator.
have to common denominator.
So what I'm gonna have to do is I'm gonna have to find the common denominator out of this. That means I will do s plus 6 times s plus 9. That's this times this and this. Plus 4s plus 9 plus s plus 6 all over.
S plus 6. S plus 9.
So what is this step right here compared to what you've been doing? You have never done that step before.
Partial
Partial
fraction
fraction.
recombination.
Yeah, it's the exact opposite of partial fraction expansion. Yeah, it's putting it back together into a single, and then can you do this? It's a little bit of math. So now how do I find h of s?
Okay, y of t.
And insert.
Divided by x.
Y of s. So it's y of
Let's see,
s.
it's
Now
input
it's
over
y of
output,
x.
output over input.
Yeah.
Y of s divided by x.
Y of x.
Yep.
Do not divide. So what's the difference between those two?
The way you wrote them.
Instead of dividing something with a numerator and a denominator like this, let's put it this way. Don't do this.
You'll get confused.
So what is instead?
And
Inverse.
time, yeah, there you
Invert and multiply. That's how you divide fractions. Invert and multiply. This is something you learned in the 5th grade. But it's pretty handy here. Now we can tell a bunch of different things. Let's see. Even without doing all of that, can you answer the question of where are the poles of h of s?
Yeah.
go. Yeah.
0 and negative 6.
0 and negative 6.
Yes. Why?
Not a negative.
Oh, wait, oh, you're right, no, not.
Because the negative 9 cancels.
Yes, because the input has an e to the minus 9t in it. So the e to the minus 9t part of the output almost certainly came from the input.
Yeah.
That came from the input. So there's 2 pieces that came from the system. And those 2 pieces have poles where? Origin and negative 6, yeah. So the system has poles at origin and negative 6, even without doing this math. Finally, is this system BIBO stable?
No.
Why not?
You have a pole here.
Yeah, a pole at the origin, yeah,
Origin,
there's a
yeah.
pole at the origin. It's not a
Yeah.
BIBO system. Okay. I like this problem because it takes the stuff you've been doing and kind of flips it backwards. It makes you think through it from a different perspective.
It's exactly your kind of problem. I
You've
swear.
learned.
You like to teach it forwards and then test it backwards.
Yeah, because what I'm testing for is, do you understand the relationships between things,
Yeah.
not just route memorization of a method? That's what I'm trying to find. Now you can memorize this. No, you can't memorize all the different methods. You just have to have some basic understanding of stuff in between. That's the idea anyway. Let's see, anything else? That's a partial fraction expansion problem. I think you can do that. Okay. I currently have not written the test. I am leaning towards some of this sort of stuff. Then probably a circuit, find the transfer function. Then probably a loop inside of a loop or something like that. Then I'm probably thinking about something that involves some transfer functions and DC gain or something like that, or possibly steady state sinusoid, something like that. And then possibly a problem like this or some mix of that sort of thing. That is kind of what I'm leaning toward right now in the test. Don't guarantee anything, but that's what was on my mind right now. So I'll share that with you. Anything else?
Sorry to ask you to repeat yourself, but what you said that you can circuit double feedback loop, a DC gain problem, you said something after DC gain.
Oh, could be steady state sinusoid. Yeah. Now, if I ask for the transient part, what I'm really asking for is partial fraction expansion. If I ask you for the transient or the steady state part, then I'm asking you to do some steady state sinusoid. The trouble is that problem can run into time pretty fast. So I start looking at those problems, and there's the type of problems that sometimes get knocked out because there's just a lot of math involved. So if I could find a way to ask that question where there wasn't quite as much math involved, I'd like to do something in that area, but sort of like that. So what did I say? I said signals to poles or step response to poles. Okay, that sort of relationship stuff. H and S from circuit. Like I say, I'm not guaranteeing this. This is just what's on my mind right now. Loop. Probably a loop in a loop or something like that. Probably two. Then something to do with DC gain or steady state. Sinusoid. And then I like this last problem that I did, something like this, and maybe something like this. Like that. And if I can combine those in some clever way, I might, something like that, because it's easy to get over too long with this. Any other questions? Any old tests you want to look at? All right. I'll see you Wednesday morning.